Welcome to the final program of our webinar series, NASA Aeronautics, Aviation at the Leading Edge. I'm Steve Ruffin, Director of the Georgia Space Grant Consortium and Professor and Associate Chair of Aerospace Engineering at Georgia Institute of Technology. NASA's Space Grant Program has consortia of universities and other partners in each state plus Puerto Rico and the District of Columbia, all focused on STEM education, workforce development, and research inspired by the exciting work of NASA's mission directorates. I want to thank Old Dominion University for hosting this webinar series and their fantastic facilities, and also the Virginia Space Grant Consortium for coordinating this series, along with NASA's Aeronautics Research and Mission Directorate. Yes, we're called Space Grant, but we have members across the nation who also work on aeronautics and aviation-related challenges. So for this series, we're focusing on the first A in NASA, which is aeronautics, the study of the science of flight. NASA has made decades of contributions to make aviation safe and sustainable by reducing emissions, noise, and fuel consumption while enhancing safety in the national aerospace. NASA-developed technology is on board literally every commercial aircraft and in every commercial airport in the U.S. We've partnered with NASA's Aeronautics Research and Mission Directorate to introduce you to the people and ideas and technology driving the ongoing transformation of aviation. Tonight, we look at the challenges of developing electrified aircraft. We'll be answering questions from our main presentation. To submit a question, use the chat feature in the web page at any time during the broadcast. Please include your first name, your major, and your university. So I'm happy to welcome Claudia Herrera, who's the Deputy Chief Engineer for the X57 Maxwell project. So Claudia works at NASA Armstrong Flight Research Center. Really excited to have you here to talk to us. Armstrong is at Edwards, in Edwards, California. And also Dave Avanesian. So Dave is the component lead for the Heather program. And Dave, I think you're going to tell us what the Heather program is a little bit later, correct?
Cool.
All right, so Dave works at NASA Glenn Research Center in Cleveland, Ohio. So really happy to have each of you here. So can we start off by you just telling us something about yourselves? Where are you originally from? Where did you go to college? And what was your major? Claudia?
Yes, thank you, Steve. As you said, my name is Claudia Herrera. I'm originally from Texas. So I was born and I was raised in El Paso, Texas, where I attended the University of Texas in El Paso.
Okay.
And I studied mechanical engineering.
Awesome. How about you, Dave?
I'm David Avanesian. I came to the United States in 2001, and I went to Cleveland State University and studied electrical engineering.
Awesome. Okay, great. Okay, so the topic for tonight. So if you think about our world right now, we've got lots of electrified automobiles, some of them fully electric, some of them hybrid. I think, Claudia, you came in here on a rental car that was a hybrid vehicle. So these are standard and all over the place. So we're here to talk about electrified aircraft. So is there what do we think we're going to gain by having electrified aircraft, and where do we stand in that? What do you think are the main benefits that we're looking for?
It's a really good thing to think about because, as you said, we are starting to see all these electrified vehicles on the road. Mm-hmm. So it's only natural that we would think what's next and what can we gain from the vehicles and apply to aircraft. Yeah. And there's a lot of questions that can be answered, and one of the things that we're looking at within NASA is what does it do to emissions? So the goal is zero carbon emissions, lower even acoustic emissions, so lower community noise. We all have experienced those very loud airplanes as they come into land. So there's some acoustic benefits. There's some reduction in costs because of the increased efficiency. And also, as I'll explain a little bit in my presentation, is we can take advantage of electric propulsion in a way that also enables lighter and more efficient structures as well.
Awesome, great, okay. Whole set of benefits there. So, Dave, any others you'd like to add or talk more about?
Sure. I think one of the main benefits of electrified aircraft propulsion really will be the benefit for the flying public, mm-hmm. and how it will decrease the cost of air travel.
Okay. All right, great. So maybe Claudia, maybe you can dive into that a little bit more. So you're working on a set of technologies, not only developing these technologies, but also looking to demonstrate them on an aircraft, the X57 Maxwell. Perhaps you can tell us a little bit about that. You know, tell us about that project. What are we really looking to learn from it as well?
Yes, absolutely. Definitely always enjoy getting to talk about what we're working on at NASA. And as you introduced, the project that I'm going to speak on is the NASA X57. And it's NASA's first all-electric airplane. And you see two names there. So Scepter is where the project started, and it's its first project name, and it's transitioned to more of the X57 Maxwell as we became an experimental airplane. And also we wanted to link ourselves more to the electric world a little bit by taking on the name of Maxwell, who's the physicist that's attributed with a lot of work in terms of the physics of electrics and a lot of the laws that we use to design electric systems. And you start to see just by looking at our project logo what we're trying to accomplish. There's pieces of it that look like a normal airplane, and then when you look at the wing, you start to see the differences. And I'll talk to what all the smaller propulsors do, which we call the high-lift propulsion system, as well as the motors on the wingtips, which we call our cruise motors. And we're going to do this by starting with the baseline airplane, which is a Tecnam P2006T, and we wanted to take this airplane so that we could do a comparison and be able to show that we are actually seeing the benefits that we expect to see from electrifying an airplane. And then what we did for what we call the Mod 1 is really just add a lot of data, or the ability to take data from this particular platform. And as we're walking through this animation, I'll pause for a second here. For Mod 2, that we then replace the conventional gas engines with the electric motors. And it doesn't look very different on the outside, but when you look at the components that are being introduced to the inside of the airplane is where you start to see the difference. So here inside of the fuselage, which I'll go through each of these components later in detail, but we added 800 pounds of batteries, and as well all the cabling and all the wires that have to then run through the fuselage and then through the wing to get to the newly electric motors that are added for Mod 2. But again, the point is that we can still be able to fly at the same points in the sky as the baseline vehicle, so we can do those comparisons and start to quantify what are those benefits gained. As we move into the modification 3 for the airplane, you can see there's a couple things that start to change. First, we removed the baseline wing and added a skinny or a high aspect ratio wing. And what this does is then it alters the flow that's occurring around the wing, so it becomes more efficient at cruise speeds. So it starts to actually affect the way the airplane flies through the sky, and it already increases some of that aerodynamic efficiency. And the other thing you'll notice is we moved the electric motors out to the wingtips, which then introduces a whole nother set of questions in terms of flight dynamics. There's a whole nother layer of questions of what happens if you lose one. How do you protect the pilot from the large yaw moment that occurs at that instantaneous loss of propulsion? And I'll talk through all of these different aspects as I walk through my slides. And finally, the modification 4 version of the airplane comes into play when we add the high-lift propulsors on the inboard of the wingtip motors. And this is the culmination of everything. So by adding the high aspect ratio wing, we increase the efficiency at the higher cruise speeds, but now we introduce this high lift propulsion system so that we can regain that performance at the low speeds and be able to do a full comparison across the flight envelope. And here is where we start to see the benefits of not just electric propulsion, but the fact that now we can introduce this concept of distributed electric propulsion. And there's a lot of benefits that can come with that in terms of the efficiency and what kind of structures we can use, but also how we can add some redundancies even to the system, which increase the safety of what we're trying to fly, which is always a big question in terms of flying electric airplanes. And this will be the final phase where we'll be able to collect data for the full flight envelope and do a direct comparison to the baseline Techno vehicle and show that we do have the benefits that we were looking to gain. I'll talk a little bit more about distributed electric propulsion, and you saw how those propellers, they extend and they retract at certain flight conditions, and that it's not necessarily a new kind of technology. It's a technology that you see a lot on gliders, but what we've done is we've coupled that with an efficient structure along with electric propulsion. Again, those benefits that we can introduce into the airframe design by having this concept of electric airplane, it really opens up the design space to an area that before maybe we hadn't looked at. And the wingtip motors are another great example of this. This is not anything new that we've looked at, but with electric propulsion, we can add that back in and also bring with it the safety features necessary to counteract some of the concerns that come up with having propulsors on the wingtips. And so you can see here on the plot that's shown on the screen just how the efficiency is able to increase with the different architectures, and you can see where X57 as a DEP type of system lands and how it compares to even the conventional general aviation aircraft, and that's already a significant improvement. I always like to show this particular graphic because it overlays the X57, the final Mod 4 configuration with all the high lift propulsors and the wingtip propulsors also included, but it shows how much smaller the modified wing is compared to the baseline wing. However, we can still achieve the same or even better type of aerodynamic performance. And DEP, as we're introducing it on X57, is really just a start, and Dave will talk more about this later, but really the goal is to eventually spread this to other modes of aviation and other sizes of transportation, because we've seen that we can really see some great improvements in efficiency, which is what we're after. Of course, with any new system, as we take it to flight, we start to run into challenges, and one of the big challenges that comes with electric airplanes is what do we need to test to show that these systems are safe and that they have the reliability that we need them to put them right next to a person in the sky. It's not just like in a car where you can pull to the side and run away from a car that's on fire. You have to deal with it in flight, which we want to avoid having to deal with it. So this is a stand that we built out at NASA Armstrong where we've tested. The hardware that you see here is actually the cruise motor that's going to go on the modification too. It's actually part of the integration process as we speak at NASA Armstrong. I talked a little bit before about the 800-pound batteries that get introduced into the system, and this is a big overview of the circuit that we essentially want to put in the sky for flight. And you can see the batteries and how they connect to the cruise motors. And one particular characteristic to highlight is the redundancy that exists, even just, again, when looking at what are those safety mechanisms that we want to employ in the design. Batteries are a big developmental aspect of electric airplanes, and we have to show that they are safe and ready for flight as well. This was one of the tests that we did to examine the battery's capability to contain a thermal runaway. And as you just saw, that did not contain the thermal runaway. This was not something that was supposed to happen, but I always refer back to Neil Armstrong's quote that we fail on the ground so that we don't fail in the sky. And this was a great find. It was something good, even though it looks bad, because this told us we needed to go back to our design and do some sort of a revision. And so we did. And in fact, the updated design worked so well. And you can see the battery here in the middle. And you actually can't see what's happening in the battery. So we had to add these IR cameras that show you what these images look like. And you can actually see here as the thermal runaway starts to propagate, the actual design that we've implemented is able to contain it. So that was a very successful piece of X57, and we're looking to build up this knowledge base with all of these different components that we're developing. One of the nice things about NASA is we're able to share all this information, and eventually that's our goal, not just to share it with the small companies so that they can also learn from what we've learned, but also with the FAA so they can also start to understand what requirements they need to levy on all these companies that are emerging with these electric vehicles, and especially when we think of the concepts like UAM and those kinds of new architectures being developed. The flight envelope, as you see here, shows what we're doing. This is the full range of the baseline airplane, and as I've mentioned multiple times now, with the wingtip motors, we gain what we call the normal operating range, so we can compare that range of speeds, and with the high lift system, the inboard smaller propulsors, we regain the slower speeds, and then we can do a full comparison. In its full culmination, this is what a Mod 4 configuration flight will look like. The airplane will take off with the high lift propulsion system active, because that's the slow speed regime, so that's where it'll need it for that extra lift. Once the airplane reaches to cruise speeds, those high lift propulsors will fold back the blades, and the cruise motor system on the wingtips will take over as the main source of propulsion. And that is what we are aiming to fly to.
That is awesome. I think I may have added something to my bucket list, and, and that is to have my own aircraft and have it be electric powered. So I'm really excited about this, especially I love the way that you've described the way in which this technology is being developed. Crawl, walk, run, and then fly. It's very exciting. So if I'm going to have this on my bucket list, I'm going to have my own electric aircraft. I realize that the X57 Maxwell is one of the necessary steps to making that happen. Can you talk to us a little bit about the timeline for the flight of that vehicle?
Absolutely. I did allude to it a little bit right now. We have the cruise motors that are going to go, or the version of the cruise motors, I should say, that are going to go in the inboard locations as part of Mod 2.
Okay.
And that is scheduled to start flying at the end of next summer.
Awesome. Okay, great. Okay, so when we look at that, that's X57 Maxwell. It's a general aviation size aircraft, so a smaller aircraft. And so it makes me wonder about larger electric propulsion systems and larger aircraft, the type that we fly commercially. So where do we currently stand in terms of that, in terms of larger vehicles, and where are we headed? And Dave, I wonder if you can talk to us a little bit about that.
Sure. NASA is investing in electrified aircraft propulsion research. And it's doing it as part of a portfolio to improve fuel efficiency, emissions, and noise levels in commercial transport aircraft. NASA is working across a range of markets, from urban air mobility, presentation of which you could have seen 2 weeks ago in this webinar, and also to subsonic transport, and working with industry partners to develop technologies and then eventually transfer those technologies into commercial sector that then they can develop future products and markets. However, the question which you actually asked, why electrification? Why are we doing that? We kind of gave top-level answers to the question. And I'm going to dive into detail a little bit more about exactly why flying public would care about this. The overall global fleet of large commercial aircraft totaled over 25,000 in 2017 and is expected to grow to 37,000 aircraft by 2027. Now, out of the 25,000 aircraft today, nearly 60% of those are narrow-body aircraft. And those are both turboprops or small regional jet. Just saving 10% in fuel consumption across that entire fleet can yield up to 5 billion gallons of fuel savings per year. And with infusion of new technologies into the aircraft, you could potentially go to 10 billion gallons per year by 2040. So obviously this is a huge improvement, and it directly impacts the reduction in cost, of course. So the main question then becomes, now we understand why we need to do that, how do we even get there? Currently we're analyzing 4 major architectures, power architectures, that we would like to eventually build and put on aircrafts. The first one is an all-electric architecture. Now that's exactly what X57 is. X57 contains a big battery with motors and propellers creating the propulsion system. Of course, in this picture you can see that it's just one motor, but in X57 will be 14 motors with 14 propellers. And that's an all-electric system. This is probably the most difficult one to achieve for large aircrafts, simply because batteries are not as good as a fuel in terms of energy density just yet. The second architecture is the turboelectric architecture. It consists of a turboshaft, or the fuel burning engine, that is connected to a generator that extracts power from the shaft and transmits it electrically to motors and propellers. The third one is the parallel hybrid, which contains a fuel burning engine as well as the battery with a motor that drives the fan. So you can see that could be all electric path as well as the fuel burning path, or both for hybrid. And the fourth is the series hybrid architecture. Again, fuel burning engines, generators, electrical battery with motors and propellers. And here you can have both turboshaft as well as the battery powering the motors to drive the propellers. So these are the 4 main power architectures that are being traded to determine which one would produce the most efficiency, which one can actually be put together in an aircraft and yield the benefits. The leading concept that NASA is currently investigating for partially turboelectric aircraft is what is known as Stark-Able, or single-aisle turboelectric aircraft concept. Now, the ABL part of it stands for boundary layer ingesting architecture. So it consists of 2 underwing turbofans. One of the main sources of drag on an aircraft is the layer of slow-moving air that builds up along the fuselage and wings as the plane goes through the air. We would like to put or embed the engines into the airframe and accelerate that air through the engine that is sitting in the back of the plane, thus reducing the drag that is produced by BLI and drastically improving the efficiency of an aircraft. This architecture, as far as power is concerned, consists of 2 underwing turbofans, which is seen here, with generators extracting power and transmitting that power electrically to the rear fuselage boundary layer ingesting fan. This has multiple benefits as architecture, because now you can actually, because you have extra thrust on an airplane, you can actually make the turbofan engines smaller, thus reducing the weight of the system. However, there are multiple technology barriers that we have to overcome. The powertrains that so far we've seen are difficult to implement. And one of the main reasons they're difficult to implement is because every component within, for example, the state-of-the-art powertrain, generator, the converters, and the motors, electrical system produces a large amount of heat that needs to be rejected. For example, in this particular picture, each of the components in a state-of-the-art in the conventional system produce about 5%, totaling over 20% to be rejected. Now, of course, if you use conventional method of heat rejection, you pretty much adding a lot of weight and kind of negating all of the benefits that you gain by electric conversion. On the project that I'm working on, which is a Heather project, we are developing a system that is really low-loss system, as well as making the system much more simple. We're removing multiple components from the path. We're going directly from AC to AC conversion, which is much more difficult to do, as well as reducing the heat generated by the system from 20% to 5%. This is the method by which we would like to actually get there. Here I'm going to give some examples of what we've done in laboratory and what hardware we've put together to actually show that it's possible. I'm going to start at the low power level. And an example I'm going to give is first the high lift motor control that we built for X57 project and delivered last year. About 3 years ago, we developed a 14 kilowatt, 99% efficient motor controller, was shown in this picture on the top left corner. The system was about 8 kilograms or so. Operated very well. However, it didn't really fit the weight margin or weight limit of X57 configuration. So we had to, in the past 2 years, redesign the system to fit the weight margins. The limit for the weight for X57 high lift motor controller was just 1 kilogram, and it had to be entirely passively cooled. So the pictures here are shown of the final design that is all put together and shipped to Armstrong for future tests. That is just 1 kilogram, that's the entire build, with a heatsink that is simply cooled by the prop wash. You can imagine a little propeller here, and as the prop spins, the air that goes around the heatsink cools the entire power system. Not only we developed the system and operated at Glenn, we also tested it extensively for flight conditions. One of which we took the motor controller and put it in a wind tunnel, and there are 2 major tests that were conducted. The first is wind tunnel was heated to 60 degrees C to sort of simulate a very high temperature environment. And the second, we simulated this at 16,000 feet of altitude. Here's a quick video showing how the high lift motor controller is driving a motor and a propeller. I'm not going to show the entire video. I just wanted to show how we were able to achieve, in its full operation, 98% efficiency, which was the goal. And you can see the power input and the output of the system. This was an example of a 13 kilowatt power system. So this is still very much in 10 to 20 kilowatt range. But on the Heather project, we're trying to solve a megawatt level problems. And there are 2 major pieces of hardware that we're developing. The first is a high efficiency megawatt motor. Now this motor is a unique motor because it's partially superconducting. The stator of the motor is just a regular stator at 1.4 megawatts, but the rotor is a superconducting rotor. But the way it's different from conventional superconducting machines is that we have acoustic cryocooler that we embedded into the rotor itself, which has never been done before. And the whole thing spins at 6,800 RPM. There are major challenges with this motor. However, we have multiple small pieces and parts that are already put together to prove out that this technology can actually work. And is currently being developed at NASA Glenn Research Center. The second is the high efficiency converter. We're trying to achieve 20 kilowatts per kilogram at 99.5% efficiency. Very difficult to achieve. However, we are currently developing the system, and hopefully we'll be able to show more results in the upcoming year. One of the major pieces of technology that we're developing at NASA Glenn is our focus on material science. It's just simply impossible to achieve these level of efficiencies and power densities without investing in material science. Here are the examples of 2 inductors that were built at NASA Glenn Research Center. And literally 6 months ago, this was just a powder. This was entirely done at Glenn, and these so far show great results. Now that we have all these components, how do we actually test them? How do you test a 1.4 to 2 megawatt powertrain on the ground? We developed a NASA Electrified aircraft testbed, which is the facility that is in Plumbrook in Sandusky in Cleveland. And I'm going to show a little animation. This test facility can support up to 24 megawatts of power, 2 megawatts of thermal management system, and it even contains an altitude chamber that can simulate for up to 120,000 feet. And even the aircraft geometries are properly implemented into the building for EMI and cable lengths. So this is the current status of high power for the aircraft.
That's pretty exciting. I love the way that a lot of this is generation of new propulsion systems, development of them, and 5 megawatt class is what you're really seeking now. And I love the way that it gets integrated into a really creative configuration as well. We don't see aircraft that look like this, although a lot of that looks similar to commercial aircraft. that propulsor on the back of the fuselage is very creative, so it's really exciting. So when do you think we might see aircraft like this in operation?
Currently, the time frame for entering into service is about 2035.
Okay.
Is what we're looking into.
Great. Okay. All right. So I have some more questions for you. I
Sure.
really want to get to them, but I just want to give out a final reminder to those out there viewing this. Please submit your questions using the chat feature on your webpage. When you do, please just include your name, your major, and your university as well. So I want to know a little bit more about each of you. And Claudia, can you tell us a little bit about your journey? I mean, how did you get to the place that you're doing what you're doing now?
Sure. I mentioned earlier I studied mechanical engineering, and while I was at UTEP studying, I learned about what was then called the co-op program with NASA. Now it's called the NASA Pathways. And it's great because, well, first of all, I got to take a break from school, and that was fun. But also, I got to get paid. I was actually doing a job for what I was learning to do and what I was enjoying working on. So that was a great way to get my foot into NASA and to start my engineering career outside of school. And once I graduated, I looked into becoming a full-time employee at what was then NASA Dryden, and I was extended an offer and I gladly accepted it. I was in the structures branch and eventually found my way into a more of a technical lead kind of a role, just by building experience and looking for different opportunities.
Awesome. Great. So how about you, Dave? What's your journey to get to the place where you're component lead now for Heather?
Sure. While I was going for my undergrad in electrical engineering at Cleveland State, I was also got a job as an intern at a private company. After I graduated with 4-year degree, I continued to work as a full-time employee in the company. So I have about 2 to 3 years worth of experience in industry. But I realized that I wanted to do something more on the research end of things. So I quit the job and went for my master's degree also at Cleveland State. I'm a full ABD. I have everything but dissertation. Right after finishing my master's degree, I went for my doctorate and finished all my coursework, research hours. I just didn't defend because the opportunity to become a contractor at NASA Glenn opened up, and I took it in 2009. Within a year, I converted to civil service. At first in the systems engineering division, working on primarily space projects. And about 5 years ago, I transferred to power and propulsion division, where I've been doing electrified aircraft ever since.
Okay, awesome, great. So what do you love about what you do, Dave?
I think the best thing I love about working at NASA and in this environment is that in the span of 3 years, I was able to work on Heather, which is a very low TRL work. So this is fundamental research, basic blocks of, in this case, power systems.
Technology readiness
level, right? As well as work on X57, which is about to fly, right? So the range of projects that you can actually get your hands on is vast. You can also lead small teams. You can be in a lab as much as you want. So just a variety of things that you can do is really, really unbelievable.
Great. Claudia, you sound excited about what you do. What do you love about what you do?
I love the people that I get to work with. I work with some very smart people like Dave. I've had the pleasure of getting to learn from some people who just have so much knowledge and who are so willing to share their knowledge as well, which is something that I've found to be very special about NASA. And I've just really enjoyed being able to learn as much as I can, whenever I can, from as many people as will share their knowledge with me.
Awesome, great. So, I'm really excited about that. I want to know, though, it cannot always have been easy to get to the position you're at in NASA. So if you thought about what were some of the biggest challenges, or what was one of your biggest challenges you faced to get to your current position, Claudia?
I had an experience where, as I mentioned, I started in the structures branch, and I was overseeing a mass properties test, And it was a very challenging project for me. There was the largest scale project, largest scale structural test I had ever coordinated, and we had a lot of challenges. We worked some really long days. It was a pretty arduous process. And at the end of it all, we found out we had some issues with the data, and the project came back and said that the data was really not what they were looking for, and they couldn't use it. And as you can imagine, that was extremely devastating, and it was a very challenging moment for me. But it was a great opportunity to learn from it. First of all, technically speaking, what it was that went wrong, what was wrong with the measurements, what was wrong with the different sources of data, and it was just a good way to also learn about myself and what kind of leader I was, and what kind of leader I wanted to be, because there's a lot that goes into failures other than just the technical things that you miss.
Right. Great, thanks. So Dave, any challenges you want to share with us to get to your role?
Like I mentioned, I was working in industry as well as in academia. I was a TA, spent a lot of time in the laboratory at university, as well as, of course, working for government. So I have a full gamut of experience, working in different environments. And I think one of the key things is to be flexible in all these positions, because industry is very fast-paced, very result-oriented, and product and profit-oriented. Where school is a bit more relaxed, a lot more research, and it's a learning environment. On the other hand, for example, at NASA Glenn, we're doing fundamental research. The likelihood of failure is very high, because sometimes things are just not going to work out. And being able to be flexible is very important. So I was able to get through all that, but it's certainly a challenge mentally to be able to actually work like that in vastly different environments.
Yeah, okay. So I'm interested, Claudia, you mentioned that you worked as an intern, and then you were in the NASA Pathways program as well. So do you get a chance to mentor any young engineers or any students as well?
I do. I'm a big believer in the concept of investing in the next generation, and I try to mentor as much as I can. Mentoring has been a part of my career at NASA since I've been there. I'm currently mentoring a few students that they themselves are now performing a mass properties test on a small vehicle that's going to get ready to fly.
Awesome. So when you work with these students, or when you think about that experience, so what's some advice you would give to students? There are a lot of students that are out looking for internships now. So how would they best maximize their internship experience? Any advice you have for them?
I would say, first of all, stay engaged. It's not just something where you show up and go through the motions of it, but you show up and you really get in there. You roll up your sleeves and you get to work. You can find people that you can ask questions, try to learn as much as possible, experience as much as possible. Just don't be afraid to interface, to reach out to as many people as you can, and stay engaged through the full process.
Okay, great. So Dave, have you got a chance to mentor any students as well? Can you tell us about that?
Yeah, I've been sort of leading the mentorship program for a lot of our projects. In the past 7 years or so, we get about 5 to 10 students every summer in a variety of our projects. And we just expanded our internship to include not just in the summer, but also in the spring and in the fall. So it's just a great time to work with students during summer. Is one of the most productive times, because they're so eager to learn and be in a lab and do things. And that's always great. So we have a lot of progress typically in the summers.
So what advice do you have for students that are planning to do internships? What should they be thinking about as they approach these positions?
Right. I think the biggest advice I can give, or two are really big advices, is don't be afraid to fail. I think it's absolutely critical. Right now is the time to do it. You're still in school. It's not going to be too bad. In all of my labs and all of my teams, we have a simple rule: if you don't burn, you don't learn. It's that simple. And another thing is just be humbled. When I finished my undergrad, I thought I knew a lot of things. Then I did my my master's and start questioning. And at Doctorate, I realized I know nothing. So then, you know, you start actually meeting smart people, and you realize, okay, there's a lot to learn. So be humbled at all times.
Okay, great. Awesome. So we're receiving some good questions here from the audience. So maybe we'll start to go through some of those here. So I'd like to read a question. This first one comes from Logan, who's an aerospace engineering major from the University of Alabama. And the question is, currently, how does the long-term battery life cycle compare to the life of regular fossil fuel-based aircraft? So how does the battery life compare with fossil fuel aircraft in their life cycle? Dave, you want to talk about that a little bit first?
Yeah, I can take that. Definitely not as good. The lithium-ion batteries, although the best energy-dense batteries we have currently available, but it certainly can compare to the fuel burning or the fuel itself. And there is a lot of research that needs to be done in the area of batteries. I don't remember exactly what the X57's flight time is, maybe 40 minutes or so, 30, 40 minutes?
30 minutes.
30 minutes. So you can clearly see that it's definitely a challenge. Not only that, they're also pretty heavy. Once you put all the safety in and actually try to make it flyable. So a lot of research needs to be done, but it's certainly an area, if you're a student and want to dive in, certainly an area that is really good to get into.
Okay, great. Anything you want to add to that, Claudia?
I would just add on that Dave hit the nail on the head. They're just not as efficient. But I do want to also add that we're fully aware of the shortcoming. And so there's lots of good research going on. Today we talked about how we integrate electric propulsion systems from the smaller scale to the larger scale. But there's also a good amount of research happening just at the battery level itself to investigate different battery technologies, because we are aware that's an area that needs improvement.
Okay, all right, great. Let's take another question. This question comes from Hamza, who's an aerospace engineering major from Georgia Tech. In terms of cost of flight operations, including maintenance, are these small electrified aircraft more efficient than fossil fuel-based aircraft of similar type? So I think this is a question for you, Claudia. So in the small aircraft range, can you talk to us about efficiency?
Yeah, and that's an interesting question, because when you look at the full model, the answer is yes. So we were just saying in the previous question that when it comes to batteries as a source of power versus fossil fuels, the energy densities are just not there. The battery cannot compare to the fossil fuels. But when you look at the full integrated model and the cost of transportation, it is because of the efficiencies that we can achieve with electric propulsion as an architecture are so much higher than fossil fuels. It's over twice the efficiency that is gained with going to an electric propulsion model. And so it's really interesting, because it actually becomes something where, again, we can take advantage of the electric propulsion systems and look at how we can change the full model of transportation. And so these smaller kind of the hopping kind of structure, or like what we're seeing with the UAM, the shorter travel spots, you really do start to see an improvement in the travel costs.
Okay, great, thank you. Okay, so our next question is from Kristen, who's an aerospace engineering major from Missouri S&T. So let's talk about flight envelopes here. What is the average expected velocity of the X57 and also turboelectric aircraft compared to conventional aircraft? So let's talk about the speed of electric-based propulsion versus fuel-based propulsion. Maybe we can talk on the larger aircraft first, Dave.
Sure. Currently, the Heather and other EAP projects are focusing on subsonic transport. So this is anything obviously below Mach 1. I believe an efficient point of flight is about 0.7 or so, 0.8 Mach. In this configuration, I don't believe the speed will necessarily change because you still have two underwing turbofans that are driving the plane, right? And these planes are still going to be very much hybrid, and the all-electric 747 or 737s are. It's going to take a while until the batteries really get there. So as far as speed is concerned, I don't believe electrical necessarily is going to make it worse or better. This is just really in terms of improvement of fuel efficiency.
Okay. Claudia, how about for other size aircraft, general aviation as well? So we're talking about general aviation aircraft that will have a similar flight speed to current ones as well?
Absolutely, and that is actually one of the goals of X57. X57, we wanted to make sure that we could match exactly the same flight envelope and all the design features that we've implemented with these new modifications are based on that. We want to make sure that whatever we can fly with the baseline general aviation, gas engine powered airplane, we can also fly with the fully electric system, because we then want to fly those same points in the sky and do the apples to apples comparison based on all the data that we're acquiring, and therefore show that we can fly at the same places in the sky, but with much higher efficiencies, which means we would use less power.
Okay, great, thank you. Okay, we have another question from Cody, who is an aerospace engineering major from University of Alabama. And I want to set this one up because I grew up right next to an airport, about a mile and a half away from the airport. So I know how loud aircraft can be. And so this question is really about noise. And you mentioned this as one of the advantages of electrified aircraft, is there was an advantage in terms of noise. So the question is, would aircraft using electric propulsion help reduce noise pollution? But the question is, by about how much? By about how much do we expect the noise to be lower?
That's a good question. It's hard to, that one's hard to answer because that one's harder to do an apples to apples comparison because, for example, X57 baseline only had 2 engines, but electrified will have 14 motors. So it's a little bit of a more difficult comparison in terms of just giving a dB that will reduce the noise. But we do know the physics are all there and the analysis is there. And we do plan on doing acoustics measurements as part of X57 flights to show this. And in particular, the landing and takeoff, as you mentioned, Steve. So those are the critical areas of flight in terms of noise production in the community. And so we do have a goal to look at that, and eventually we'll have actual measured data that we'll be able to compare, but with the caveat that you're comparing 14 versus the 2. So the answer is yes, because we can do the analysis and we can show on paper that the acoustics emissions are reduced, but we just need to keep in mind the configuration is changed as well.
Right. Anything you want to add to that, Dave?
Yeah, I think one of the cool features, for example, of X57, it's really cool, the fact that you have distributed electric propulsion on that wing. You can actually potentially do an advanced control on those propellers, where one propeller is sort of out of sync by about 180 degrees with another propeller. And of course, as the acoustic wave is produced by one propeller, the other one will just simply cancel it. So that's a really cool test that you can actually do on a distributed propulsion, electric propulsion system. So I think there is a lot of research that can be done for electrical systems in noise reduction within them. So, and I think the physics is definitely there. It's certainly quieter. By how much it's difficult to determine, and a lot more testing that has to be done.
Okay, great. So one thing that comes to my mind is, you know, the aviation industry has become quite safe. I mean, it's a very safe mode of travel compared to many others. Not perfect, but pretty safe. So about this thermal runaway thing, can you give us some projections of safety of electrified aircraft compared to fuel-burning aircraft? Do we expect safety enhancements in some way relative to fuel-burning aircraft, and what concerns do we have that are things we need to work? So maybe Claudia, I'll go to you first to talk about that.
Yeah, it's a really interesting question. I mean, when you think of even just to fly here, right? I had to make sure that all my batteries were with me in the main cabin. You can't put them in your checked luggage. So, but then we want to take a big 800-pound battery pack and put it behind a pilot and go do flight testing. So we are aware that there are some safety implications when it comes to electrifying an airplane. So we have to figure out what is the right level of testing to have the confidence that these systems will be safe in flight. And it's also important to note that it's more than just the battery. The battery is a good example of how we've done some improvements in the design of those components. But there's all the cabling, all the wiring. That's some high voltage that we're talking about, running power to those motors. So you have all the cabling going out to the motors, and then the motors themselves, there's a lot of heat production there that we need to keep monitoring. So we do have a ways to go. Obviously, the conventional gas propulsion has quite a legacy that it has been behind, but at one point, it's also important to note that at one point, that kind of flight was considered unsafe. And there was a lot of questions and a lot of uncertainties around gas propulsion. And now it's like you said, it's pretty commonplace, and we do it every day. And so it's a similar pattern where we need to go figure out what are the questions that we need to ask, and what are the tests that we need to run, and what are the policies that we need to implement to give the confidence that these systems will be safe, because we need to ensure that by no means is safety compromised by going to an electric type of propulsion system.
Great. Okay. Dave, how about you? Any other thoughts you have about safety? And I mean, what if a propulsor fails? What happens? Or?
Right. So I think people really should keep in mind that we're entering a whole different paradigm here, right? The electrical propulsion on an aircraft is not something that it's really new. We don't have hundreds of thousands of hours of fuel burning engines worth of data to know exactly the reliability of the system and where exactly the failures might come. We do know that motors and, for example, inverters or power converters are certainly not as reliable at this point. And there's a lot of work in the reliability that needs to happen. And it's certainly in the radar of all of the work that we do. We do follow very strict requirements and they do make the development of the systems much more complicated because of that. Now, to directly answer the question, what happens if something fails? Now, in the case of, for example, the star cable configuration, even if the propulsor in the back fails, the plane just becomes less efficient. It still flies. There is really no risk in terms of the catastrophic failure. On X57, it's actually great because you have so many propellers. Even if a couple fail, it's not a big of a deal. And so there is an inherent safety that is built in within an electrical system. And I think that's a benefit that we can certainly yield from going to electric propulsion.
Okay, great. All right, and I'm curious, remember I have this bucket list thing. I'm going to buy an electric airplane, right? So is NASA working with commercial partners for, say, general aviation class vehicles in this work? Or are there others that are really interested in building these and selling them?
Absolutely. It's not too uncommon to open up Av Week and hear about another company that's actually taken an electric airplane to flight. So you see them in flight already. There are a lot of companies that are interested in this. Our prime contractor is a company named ES Aero, Empirical Systems Aerospace, located in California. And they've actually been working with various other companies. Our motors, the cruise motors, are from a company called Joby Motors. And so they're very much into the electric motors, as well as controlling the motors, the motor controllers themselves. And there's the batteries actually come from a company called EP Systems, Electric Propulsion Systems. So there's quite a bit of interest in this. We know this is coming, so all the small businesses are getting in the game.
Okay, great. Sounds exciting. All right, so let's take another question. So this question comes from Chris. who's majoring in engineering physics and applied math from Hampton-Sydney College. So this question is more about aerodynamics associated with the X57. So how does the 2D profile wing design for the X57, what does that look like in airfoil design? Is it similar to other NACA airfoils, or was it something that's created just for this vehicle?
Oh, that's a really fun question. It's a pretty standard airfoil. There's really nothing special about this two-dimensional there's nothing special about the two-dimensional airfoil for X57. The only goal was something that was a lot smaller as a lifting surface, and it's made of composite, so we still wanted to make sure we had good manufacturability for the wing, and we wanted to maintain laminar flow. So those were pretty much the only requirements that we had. There's really nothing special about our airfoil.
Okay, all right, great. And let's take one more question here, and this question is a bit about spin-offs. So NASA does a lot of research, has done research for decades in many things, and if you look at the space program, there have been lots of spin-offs that affect all kinds of other industries. So this question comes from Chase, who's an aerospace engineering and mechanics major from University of Alabama. How can we apply the challenges of alternative propulsion to the automotive industry? How does the alternative propulsion carry over to other industries? So are there things that we're learning here that are going to affect other industries or improve other industries? So Dave, you want to take a crack at that one?
Sure. I think that there is a lot of, all of the technologies we talked about are very tightly coupled. For example, electric motors are a field of study that are common for cars as well as airplanes. I think that this is one of those technologies that if you develop it, it really is going to be beneficial for both completely different areas of engineering. Another one is power electronics. Power electronics is common for both. I mean, packaging perhaps and operation in high altitude is of course different comparing to cars. However, the basics of how you build it is the same. Of course, the battery is very similar. Again, it's depending on what level of technology readiness level you would like to do the research in, right? Mm-hmm. If you are working on packaging and actually putting it in flight, it will be a bit different than actually putting it on a car. But if you are more on fundamental basic research, of course, that's basically the same.
Great. All right. Thank you. This has been fascinating. So I really want to thank you, Dave, and thank you, Claudia, for what you've talked to us about here today. Especially the advice that you're giving to students, I think, is very powerful. So this webinar has been recorded and is available on the series website along with the first two programs in our series. So before we sign off, I want to share some key resources with you and some other opportunities for those in the audience. So be sure to visit the Learn More section of the website. There you will find technical papers recommended by subject matter experts here and information on a wide range of student and faculty opportunities through NASA and also through the NASA Space Grant Program. So the page that you see now provides a link to connect with NASA Space Grant in your state. So there's a NASA Space Grant Consortium in every state, plus DC and Puerto Rico. And there you can learn more about scholarships, fellowships, internships, student flight and design programs, faculty research and curriculum projects. Also, pre-college enrichment programs offered for students and also for educators. Space grants are a key link to NASA in each state. So explore the websites that you see and connect with programs in your state, DC, District of Columbia, or Puerto Rico as well. So NASA internships. NASA offers paid internships through the agency's 10 centers around the country in its NASA Internships and Fellowship Program, as well as fellowships for graduate students. The program website offers more information on these programs and how to apply. NASA internships and fellowships are available to all U.S. citizens. In addition, the NASA Aeronautics offers a special opportunity called University Leadership Initiative I want to talk to you a little bit about. So this opportunity is different from other research grants. They fund teams led by universities that get to propose what they want to research. After 2 rounds of awards, NASA is engaged with 34 universities so far. The key is the universities lead as long as the topic is related to NASA's work. So far, solicitations go out annually via Inspires, that's NASA's online system. On behalf of the NASA Space Grant Program and the NASA Aeronautics, we really thank you for joining us this evening. Thank you, Claudius.